my name is Ike, and I will be talking about Diaframe, which is joint work with Robert Grebbers and Herman Geuvers. So for Diaframe, what we're interested in is verifying programs that use fine-grained concurrency. So here you should think of implementations of locks, such as pin locks or ticket locks, or concurrent data structures, such as the Triber stack or the Michael-Scott queue. Now, if you write such a program and you want to show this is correct, there are various tools available, but they basically fall into two categories. So on the one hand, you have automated tools, such as Voila, Caper, and Starling. And here you need to spend relatively little user effort to perform this verification. However, these tools are typically less expressive, and you need to trust that the authors did a good job in the implementation of these tools. On the other hand, you have foundational tools embedded in a proof assistant such as Coq. Examples are VST, Iris, and FCSL. Now with these tools, these are very expressive typically, and they give strong guarantees. However, they usually come with the obligation of a manual proof. And if you need to choose between little user effort or more user effort, you're typically going to go for the left way. So with Diaframe, we try to fix this problem. And we built a tool called Diaframe, which is both automated and foundational. And this gets the best of both worlds, we think. So we get an expressive framework with strong guarantees and still requiring little user effort to perform these verifications. So how did we get there? Well, we built on top of existing work on such verifications. Specifically, we built on top of Iris, concurrent separation logic inside the Coq proof assistant. Now, Iris already comes with, is very expressive, and as a soundness proof, the only thing which is really missing there is good proof automation to do these verifications. And also, we did not just want any proof automation, we want automation that satisfied some requirements. So we wanted automation which is extensible, so you can perform verifications using some custom resources if you need those for your program. And we also wanted automation without global backtracking. This is important if you want your verification to fail quickly if you made some mistake. And it also is nicer to work with if you are doing interactive proofs. All right, so yeah, the thing we built, I think, satisfies these requirements. And to test that, we evaluated on 24 examples from the literature. What we did is we compared the proof burden of Diaframe to that proof burden of some existing tools out there. We found that it's quite comparable. So even though we are inside this stronger tool with stronger guarantees, we don't necessarily have to spend more effort. And if we compare the proofs in Diaframe with those in plain Iris, we see that we get about 90% reduction in the proof size. And to attest the expressivity of Diaframe, examples we verified contain all the examples run in the benchmarks of these other tools. So most of the examples you can verify mostly automatically in Diaframe. To give you some example on the scale of this automation, how much the proofs get shorter, here's an example from the verification of the release of a ticket lock, where above you see the manually written proof, which basically gets replaced with a single tactic to prove this or triple. So yeah, what we're really trying to prove in the Diaframe are these OR triples, where we have a precondition P, want to run an expression E and show that in all these cases, the postcondition satisfies Q. And the usual approach to perform such verifications is to use symbolic execution. The idea is then that when you look at E, you can determine a unique proof rule to apply and continue the proof. However, in Iris with fine-grained concurrency, the proofs rules you can apply are not necessarily unique. You can apply one of several, and in different cases, you may need one or the other. So how did we overcome this? Hello? Right. So on the left, we have the Hoare triple we wish to prove, and we want to end up at QED, where the proof is actually finished. So instead of trying to get there directly with symbolic execution, what we do is we formulate and prove more syntax-directed versions of the Iris proof rules to end up in some intermediate goal. Now, this intermediate goal is nice because we found a goal-directed proof search procedure on such goals, which either lets us end up at another Hoare triple or finishes the proof. Now, there's a bit of a tension going on here. On the one hand, we want the intermediate goal to be simple so that the proof search procedure is easy. On the other hand, we want to support as much of the Iris rules as we can, which makes the intermediate goal format a bit harder. All right, so I mentioned we cannot do symbolic execution directly. Let's investigate a bit why that is the case. So here at the bottom is a Hoare triple we may wish to prove. So as a precondition, we have that L maps to some value n, and then we execute fetch and add, which will fetch the value stored in L, add 2 to it, and then store n plus 2 back inside L, and then return the old values stored in location L. All right, so what symbolic execution will do is replace the precondition with the effect of this fetch and add statement. So if we want to prove this by symbolic execution, our next goal will look like this. And this is, of course, easy to prove, and then we're almost done. Let's now look at an example which we run into in proofs in Iris, where we don't have this L maps to directly in our precondition, but instead have an invariant. So this box I means it is invariant that resource I holds. And this is these invariants are one of the key ingredients which allow Iris to perform verifications of programs with fine-grained concurrency. So in this case, our invariant is that L maps to some even number, and all threads are able to use this fact, but also must uphold it. So the reason why this Hoare triple is true is whatever the even number was before, if we add 2 to it and store that back inside the invariant, or store that back inside location L, still going to be an even number. Now, if you do symbolic execution, this will fail, because by looking at the precondition, there's no L maps to statement in there directly. So how does this proof go in Iris? Well, what you first do is open the invariant. So here you see that the box I gets replaced with just I, but now in the post condition, you must show that this invariant still holds. Now this rule is true because the fetch and add operation is atomic. And so if the invariant is temporarily broken, no one else can witness this. But this invariant opening rule is applicable for all invariants and for all atomic operations. So it's kind of hard for automation to figure out when to apply this rule. So we came up with syntax-directed versions of these rules. So what does Diaframe do when it sees this goal? Instead of proving this Hoare triple, we go to this intermediate goal format of this shape, which looks a bit scary. So let's go over it one by one. So we are proving an entailment in separation logic, where we can assume this invariant, and then behind the entail symbol, we get this arrow symbol called the fancy update, which is another ingredient of the Iris logic. And this symbol basically allows us to still open invariants if necessary. Now, the next thing you should notice is this L maps to Z, which is behind the turnstile, so it's part of our goal. It's a proof obligation. And this is the precondition of the fetch and add operation. Okay, so we have this difficult-looking goal. Why is this nice for us? Well, if we look at our goal, we see L maps to Z, and if we look at our hypothesis, typically and specifically inside this invariant, we see that these hypotheses are actually relevant. We can syntactically see we need to open an invariant in this case. So this brings us to the next part of Diaframe, the goal-directed proof search on these goals. So this is the goal I showed you before, and now I'm going to substitute this I back in and remove irrelevant parts. So the goal we wish to prove looks a bit like this. Now there's other goals which may also appear of a different shape. And if we look at the literature, we can use ideas from logic programming and from the refined C paper from PLDI from last year. And the idea is there that we can look at the connectives in our goal and interpret them as proof search instructions. Now this, the way they do this in previous work worked really well also for us in the case of the for all symbol or the magic wand, but in the fine-grained concurrency case, it does not work the way they did it before for existentials and this fancy update. So we needed to do something different. The basic idea here is that we look deeply inside the hypothesis and the goals we have. So we look inside the invariants beneath the existentials on both sides and find the maps too. And this works for this case, but it also works for the case where we directly have the maps to in our context, or if we have the maps to with some other resource B. As soon as we find this match, we find a way to use the relevant hypothesis, and we can capture this using a generalized notion of bi-abduction. So all these cases are automatically detected. Additionally, you can extend when you think two things are relevant to each other. And also important, once we find any hypothesis which seems relevant, we will try to use it and never backtrack on this choice. All right, so we talked about the syntax-directed versions of the iris proof rules and the goal-directed proof search. In the paper, you can find additional details on how we dealt with ghost state, which is another key ingredient of how iris is able to verify programs with fine-grained concurrency, give more motivation of the goal format, and specifically show how we use bi-abduction. And of course, you can find a more detailed comparison to other tools. So to conclude, I present a Diaframe, a tool for verifying fine-grained concurrent programs. It's foundational, being built on top of the iris framework for separation logic, and it's automated using ideas from bi-abduction and logic programming. And we found that the proof burden of Diaframe is comparable to that of existing tools. And with that, I'm happy to take any questions.
Hi, yeah, whoa, great work. I'm curious as to if you're familiar with other proof automation tools in Coq, in particular like Coq Hammer and Crush, and I guess how those compare with the automation of your system.
Right, so I cannot say I've used Coq Hammer or Crush. I think one thing I can say is that so the proof automation I've built here is really focused on the separation logic, and I think some of the rules we use are also really well suited to separation logic and maybe not very well suited to generic proof automation. So one thing which we leverage a lot is that like these maps twos, they're always, one of them is around. And so if we find a maps two and need to prove it, then most definitely that's the rule you're going to want to use. And I think in more generic proof automation, this is not the case. You might have several good options, and in some cases you need one, and in the other case the other. So yeah, that's one thing I want to say.
This looks really cool. I'm wondering what happens when the proof automation fails. Do you get, the automation may have succeeded through some prefix of my program and then it fails, and what sort of goal am I presented with at that point?
Yeah, great question. So indeed, the proof automation in some cases is not able to completely solve a goal. And in this case, it will basically stop at the moment it does not know how to proceed. And so depending on the case, you might see just a goal you're familiar with from basic iris, or you might see something which is a bit more complicated. I have examples of this in the paper, but we tried to make these goals which are presented with somehow still readable. And so I feel that it is possible to still figure out what went wrong and how you can proceed. So it's also definitely possible to see, hey, the automation stopped, then do some manual proof steps, and then continue the automation when you're finished.
Some decision that the automation made?
So I mentioned no backtracking. The tactics I built there's basically two variants. One will never do backtracking, and the hints should be set up in such a way that the choices made before are always correct. And in practice, I feel this is also true. There's also the one that will backtrack when you specifically ask for it. And in this case, yeah, it's possible you end up in a state you don't want to end up.
Hi. Yeah, this looks really cool. Have you tried applying it on proofs with atomic triples at all? My impression is that's where you have a lot of non-obvious implications.
Yeah, thanks. I have tried it as part of ongoing work. And what I noticed that proofs of these atomic triples tend to be more interesting, and that sometimes it is the case that the automation will apply something and then you don't want to do that. So this is kind of hard to figure out the balance between do what seems right and in the case of atomic triples maybe delay that a bit. The techniques do seem applicable, so I think you can improve the existing proofs of these atomic triples with techniques such as these.
I wonder if I assume that your framework is generic to the language. I wonder what is the difficulty if I want to use it for some non-traditional other than points to assertions.
So the question is, what if I want to use it for resources other than maps to?
Yes, some language which have more than just points to.
So Diaframe is extensible, and what you can do with these custom resources is you can give hints. So for example, this is what we do for a ghost state, where we have maybe some piece of ghost state which is related to some other piece, but it's not directly obvious how to get from the one to the other. And so then you can give a hint saying, if you want this and you have this, then you need to find this additional side condition maybe, and then after doing the lemma, you get some additional resource. So you can instruct the proof automation how to deal with your custom resources, basically.
Okay, thank you a lot. Let's thank Ike again and have the next speaker set up.